Welcome everybody. Let's talk about doing calculations involving light. Okay, there's actually two calculations and two relationships we're going to be looking at. The first is the relationship between wavelength and frequency. And the equation you need is written down below. C equals lambda times nu. Okay, let's translate that. C is the speed of light. This has a value of 3.0 times 10 to the 8th meters per second in a vacuum. This is a constant. So this number will always be the same. You always know it. Just need to remember that C is 3.0 times 10 to the 8th. Lambda and nu. Lambda, the Greek letter lambda, represents wavelength. And because the speed of light has units of meters, we will have to use our wavelength in meters in this equation. So if you're given that value in nanometers, you'll have to start by converting it. The fancy looking V is the Greek letter nu, and this represents frequency. And frequency has the units of hertz, which is cycles per second, or inverse seconds, which we can write as 1/seconds. You'll typically see it written as hertz though. So this relationship means if I know any two of these values, I know the third. Since I always know the speed of light, if I know the wavelength, I can calculate the frequency, and if I know the frequency, I can calculate the wavelength. Let's look at one example. Let's calculate the frequency of light with a wavelength of 575 nanometers. The first thing you'll need to do before we can use that wonderful equation up top is convert from nanometers to meters. I'm going to remind you that 1 nanometer is 1 times 10 to the negative 9th meters, and you can do this conversion either using proportions or dimensional analysis. I'll use dimensional analysis right now and do this conversion. Once you have your wavelength in meters, you can plug it into your equation involving the speed of light and solve for the missing variable, which is going to be our frequency here. I've plugged my numbers in. In order to solve for the frequency, I need to get it by itself. Right now it's being multiplied by the wavelength, so I'll divide both sides of the equation by that wavelength. Solving for frequency, I get the value 5.22 times 10 to the 14th hertz. We're done. The second relationship we're going to look at is the relationship between the frequency of light and the energy of a single photon of that light. Our relationship is written as capital E equals h nu. Capital E is this energy of a photon of light in joules. H is Planck's constant, and this has a value of 6.626 times 10 to the negative 34th joules times seconds. It's worth pointing out that this is another constant. You always know this value. Nu is, of course, our frequency in hertz. This equation allows us to calculate the energy if we know the frequency, or the frequency if we know the energy. So my example down below says calculate the frequency of light with an energy of 3.6 times 10 to the negative 19th joules. We're going to take our equation, plug in the values that we know, and solve for the missing variable. Once again, I've gotten to this point where I plug my numbers in. In order to solve for the frequency, I'll need to divide both sides of this equation by Planck's constant. This gives me a frequency of 5.43 times 10 to the 14th, and our units are going to be hertz for frequency. The last example I want to put it all together. We can use these two equations in tandem. So for example, what is the energy of a photon of light with a wavelength of 455 nanometers? We are told the wavelength. We can use that to find the frequency. And then once we know the frequency, we can find the energy. So we're going to have to do the whole process. Remember, you're going to have to start, and before you can calculate frequency, by converting from nanometers to meters. Let's do that right now. Once we know our wavelength, in this case 4.55 times 10 to the negative 7th meters, I can use this in the equation involving the speed of light in order to calculate frequency. And then once we know that frequency, we can calculate the energy of a photon of light using our energy equation. In summary, we have an equation that relates the wavelength and the frequency. And so if you know one, you can find the other. And we also have an equation that relates energy and frequency. And so once you know frequency, you can calculate energy, or you can work your way backward. Please make sure before you use the equation involving wavelength that you have converted your wavelength into meters. Because the speed of light is in meters per second, you must have your units match within any problem.